Hello, my name is Keiller, and I'm here to present our work, Prototypical Contrastive Network for Imbalanced Aerial Image Segmentation. There are several applications in the remote sensing domain that are interested in identifying one specific object in the images. And this is to better study or to monitor that object. For example, here on the left we have the segmentation of rivers, maybe to just monitor the rivers over time. And on the right, we have the segmentation of cars, maybe to better study the traffic. Such a problem is usually modeled as a binary segmentation task, in which the main goal is to classify each pixel into two classes. The foreground or positive class, which is actually our class of interest, and the background or negative class, which is everything else. All right? So for example, here on the right, we want the foreground class is the car class, is our class of interest, and the background class is everything else that we have in this image. So the background class here is actually composed of houses, buildings, trees, forests, and everything else. The problem with this modeling is, one, the background class is not clearly defined because the background class is actually composed of distinct properties, of distinct categories, And so, for example, here, as I said, the background class is composed of houses, trees, and everything else. And because of it's not clearly defined, it's really complicated to learn a good representation for the negative class. And the second one is the class imbalance, and because the negative class is actually composed of several samples, it usually has way more samples than the foreground class, and we can clearly see this here. As we can see, we have way more negative samples than positive samples. Most works in the literature dealing with this problem try to learn a good representation for both classes, the positive and the negative. And the problem with this is that learning a good representation for the negative class is really complicated, it's really difficult, because as I said before, the negative class is actually composed of different categories, classes from different categories. And also, most of the approaches, they don't take into account that although the negative class has way more samples than the positive class, only the hard samples are actually valuable for the learning process. All right? And because of the dissimilarity between the positive and the negative class, the hard negative samples are usually much less than the easy ones. So taking this into account, in this work, we propose a novel approach to perform imbalanced binary semantic segmentation that focuses on the positive class, easing the learning process. And on top of that, our model has an intrinsic mining system that mines hard negative samples and alleviates the imbalanced data issue. So talking about the proposed approach, we start with an image. We have a fully convolutional backbone that extracts features for this image. In this case, we actually extract features from multiple layers. We upsample them and then we concatenate these features. And now with the feature maps, we actually project each pixel or each pixel representation into an embedding space. In this example here, green represents positive class or the class of interest, while red represents the negative class or the background class. And so we project each and every pixel into this embedding space. We can also see in this embedding space we have a star, which is actually the prototype for the positive class. In this example here, we only have one prototype, but we could have more prototypes for the positive class. But the important thing here is that we only have prototypes for the positive class. We do not have prototypes for the negative class, because the learning process that we're going to do here is to actually pull the positive class closer to the prototype while pushing the negative classes apart from the prototype. All right? And so by doing this, we want to make the positive class similar to the prototype or more compact. And we're not interested in learning a good representation for the negative class. We are actually interested in making the negative class as similar as possible from the prototype. That's it. And we do that optimizing this loss function here that is actually based on the distance between the representation and the prototype, and also has a margin to define when the sample should be pushed apart and when a sample should be pulled together to the prototype. The margin is also important during the inference because it's based on the margin that we classify a pixel as a positive or a negative class. All right. So that's essentially the idea. As I said, the most important thing here is that we only have prototypes for the positive class. So we want to learn a good representation for the positive while making the negative class as similar as possible. And this alleviates the training process. Talking more specifically about the protocol, we tested our approach using two data sets, the wagon, in which we want to segment car, and the river, in which we want to segment water bodies. We used the fully convolutional DenseNet 1-to-1 as our backbone, and the Euclidean distance for the loss function. So here we have examples of the two data sets we used. And here we have the results. So the y-axis here is the F1 score, while the x-axis is the training time in hours. And as we can see here, our method outperformed all the baselines, producing a better result in terms of F1 score, but taking less training time. So for example, for the wagon dataset, our approach produced 79% of F1 score, but while taking only 8 hours to train, while most of the baselines got around 75% of F1 score, but taking 20 hours to train. The same thing for the river dataset. We got 78-79% of F1 score and taking only 60-70 hours to train the model. But most of the best baselines that we got here, they got around 70-75% of F1 score, but more than 100 hours of training time. So our method can actually outperform the baselines not only in F1 score, but also in the training time, in the speed of the training time. Here are some qualitative results. So the image, the ground truth, the best baseline result, and our approach. For the baseline and our approach, we are actually using an image here that has the true positives, negatives, false positives in red, and false negatives in green. So we can clearly see that our method produces fewer false negatives and false positives, being better balanced. For the river dataset, so the image, the ground truth, now the image and the best baseline, notice here that this is a huge image, and we can see in this case of the baseline a bunch of red dots, and we can see a lot of green, which are actually false positives and negatives. And for our baseline, which is this image, we cannot see a lot of green, and we also see less red as well, showing better performance. Lastly here, I want to just show our embedding space. So on the left here, we have the baselines, and on the right, we have the proposed method. The black star is actually the prototype, and we can clearly see that our method produces a more compact embedding space, which might be advantageous in some cases. All right, that's it. Thank you very much. This is where you can find the project page, where you can find the code and everything else. So thank you very much.